This morning, we were kind of going between, single node systems and then distributed protocol. And now I'm going to toss you back into thinking more about single node systems and kind of challenge the idea of going distributed and talk about why simplicity is the new black. So a little bit about myself. I was a founding engineer at MotherDuck, and MotherDuck is a cloud data warehouse built on top of DuckDB. And I kind of figured out that most of you know about DuckDB, but how many people heard about MotherDuck? Just show of hand. Okay, awesome. That makes me very happy. So I was there for about 3 years and worked on getting the product from 0 to 1. And I really, really had a great time. And then earlier this year, I transitioned to MongoDB and started working on larger scale distributed query execution engine. So I think this type of experience gives me a very special vantage point, on different types of systems, their constraints, and the design principles, etc. So working at MotherDuck, I think one of the things is it kind of really reshaped how I think about systems and system designs in general. It got me very interested in single node architectures. So for example, SQLite is one that's been more established, and also the newer comers like DuckDB and DataFusion. And these are kind of like the single node architectures popular in the data infrastructure world. And it kind of got me to think a lot more about how hardware has changed and how far you can push the boundary of data analytics with these single node systems. So resisting the urge of going distributed. I'm not saying that you don't need to go distributed or distribute your system, but on the other hand, it's more like, let's look at the state of the art and kind of dwell on that idea a bit more, right, before we actually go distributed. And before I jump in further, I just want to clarify what I mean by going distributed. Right? I'm not talking about consensus protocol over here, like Raft and Paxo. Right? Those are kind of replicating state for availability and fault tolerance. They're distributed, but they don't really typically incur the cost penalty because they're not parallelizing compute across machines. And that's something that Frank Sherry proposed in a cost paper. We're talking about sharded systems here, where we're kind of scaling out compute and data across multiple machines in a cluster, and this is when things can get a lot tricky. So here's today's agenda, so you don't get lost. As I talk about all these different things, we're going to start at the hardware level, the foundation of what everything runs on, because I think it's super important to kind of understand how hardware has transitioned and progressed over the last decade. And then we're going to move one layer up to the software level and kind of look at how some good software design is sort of aligning itself with the hardware progress. And then we're going to move to the application layer to understand the workload patterns that supposedly should guide us on our system design and adoption choices. I imagine most of us here, we're not just system designers, we're also system consumers. Oftentimes, you're both designing something and picking a system to use at the same time. And that decision should be guided clearly by the application requirements. And then we're going to move from the technical to the human layer because, like Yoram mentioned earlier, right, it's not all about engineering. There's the art of it, and further, there's a human of it, right? In the end, is us humans kind of making these choices. So our own anxieties, biases, incentives, habits really guide the system choices that we make in terms of building and adopting. And then finally, we're going to tie it all together, and we'll talk about the type of system architecture I believe will really drive the next wave of innovation in both data and AI, and how that looks like. So let's get started at the bottom of the stack with hardware. So here is a fun comparison, right, of the hardware back in 2013 versus in 2025 that cost the same amount of money. The point here is hardware has gotten ridiculously powerful and cheap. And I want us to really look at the specific numbers to get a concrete idea of how hardware has improved. So back in 2013, you need a stack of servers, to do something that basically today you can accomplish with a single modern server. On the CPU, for example, right, it went from 16 cores to 96 cores. That's roughly 6x improvement on CPU. And you also take advantage of the architecture improvement on those CPUs. On the RAM side, we used to have 128 gigs of RAM. That's considered very, very good already. It's top-notch hardware. But now you can easily get 2 terabytes of RAM on that machine. And on the storage side, we went from 1 terabyte of SSD to 30 terabytes of NVMe. That's about 30 times, improvement on storage size. And also, we have improvement in the throughput aspect. So it went from 500 megabytes per second to 14 gigabytes per second, right? That's also roughly about 30x improvement. And GPU compute is one that really, really improved over the last decade. Now, teraflops is something that measures the number of computations a GPU performs per second, things like additions, modifications. And now that went from 2.5 teraflops to now almost 2,000. That's an 800 times increase in terms of GPU compute power. And then on networking, we went from 1 gigabit per second to 100 gigabit per second. That's 100 times the increase. So the point here really is everything has gotten ridiculously better across the board, from the CPU, from the compute, to the memory, to storage, to networking. Right? So what you had to use a rack of server to accomplish back in 2013 can now be done using one machine in 2025, right? So that's great. And this is all really driven by this Moore's law that I'm sure a lot of you have heard about, right? So the Moore's law states that the number of transistors on a microchip doubles every roughly 1 to 2 years. And this really helps exponentially increase the compute power and reduces the cost of that compute, of those microchips. And it's not just about packing more transistors to your microchip. It's also about the compounding improvement in terms of CPU, memory, storage, and bandwidth over time, like we saw earlier. Right, so this is kind of the fundamental reason that has driven all of the progress in software and hardware over the last decades. From things like PC to mobile to cloud computing and now AI. And so here is a quick comparison again on this compounding impact of the Moore's law, and just to understand how much efficiency has improved because of the transistor count. But it's not just about the transistors, right? And what's also extremely exciting to me is that the hardware has gotten more accessible. This improvement isn't just happening in data centers. This is also happening to the hardware that we own and have. This is the laptop that I am presenting from. Nothing fancy, but I have 48 gigs of memory and 1 terabyte of SSD, which means I can run easily queries, complex query analytics right from my machine over 100 gigabytes of data with nice software like DuckDB. So that's something that you used to have to do a few years ago with perhaps a server provision from somewhere else and multiples of that. Right now, it's all very much sitting on your laps. So that realization really helps you kind of start to think, right? How am I supposed to then take advantage of that hardware improvement when I design my software? Because good software is riding that wave of the improvement on hardware. For example, DuckDB, right? DuckDB is excellent example of a very powerful single node system that is fully leveraging that improved hardware. This is a Raspberry Pi device that costs about $35, and you can run TPC-H benchmark queries, which are complex analytical queries with DuckDB with a scale factor of 100. So that's about 100 gigabytes of data. And I just spoke with someone from DuckDB Labs during break just now. They just did an internal benchmark testing that if you give DuckDB more hardware, more resources with a bigger EC2 instance of more cores and more RAM, you can actually run TPCH benchmark with scale factor 100,000, which is the max you can run TPCH benchmarks with, and that's 100 terabytes of data, which means in data analytics, at least, right, scaling out may be irrelevant from here onwards if you understand the hardware improvement and know how to design software that can fully take advantage of all of these threads running on your single node. So here is a lesser known Moore's law, which is the second law, also called the Rock's law. And it states that the cost of a semiconductor chip fabrication plant doubles every 4 years. Right? What this means now is that only a few companies can afford to make the most advanced chips, like these GPU chips. And these days, a typical fabrication plant costs about $20 to $30 billion per site to build. And that's extremely expensive. But now that also means that a lot of R&D dollars has gone into improving these chips. And what are these chips now improved for? Obviously, single node performance, right? You have a lot more cores on there, a lot more memory, a lot more bandwidth. And if your software is able to leverage that improvement, you're basically riding on trillion-dollar R&D dollars for free, right? And you shouldn't really think about, how do I leverage that very specialized GPU chips that's going to come in the future? Because even today, you already have extremely powerful chips, and the systems you build should be able to leverage that amazing capabilities that's already with us here today. And now, we looked at how hardware has advanced, and we looked at how good software is taking advantage of the great hardware progress and making themselves more efficient, leaner, and running on these powerful chips. But software doesn't exist in a vacuum, right? They exist to solve problems, to do work. So I think understanding workload patterns on the application level should also help guide our decisions in terms of how we build a system and what systems we actually adopt. So now here's an example of, around data analytics on how, a simple truth about workload patterns. And this is one of the founding principles that really motivated the beginnings of MotherDuck. And the simple truth is that most people are not running analytical queries on big data, right? So it was very convenient that I think 2 years ago, maybe around 1.5 years ago, the Amazon AWS Redshift team published this data set that's composed of 500 million queries over 32 million tables, I remember, and over a 3-month period. And this is the data set they gave to the public, and it's completely open source. And the MotherDuck people ran some analysis over this data. And once you analyze it, right, the outcome becomes quite clear. We consider the top 2 rows highlighted in yellow here, big data. And you can see less than 1% of people are actually running analytical queries on big data. Right, so understanding that workload tells you now that most people's workloads are lightweight and things that you can easily accomplish with something like DuckDB on a single node. So I think MotherDuck, or systems like MotherDuck, really embodies this type of realization that better and cheaper hardware with more powerful single-node systems, right, and not big data workloads will lead to a simpler, faster, cheaper era of data infrastructure. So we start to see, some of the companies who are, kind of forming around this idea and really kind of taking advantage of what's changed and what's happening out there. It just means that you really don't need a cluster anymore to accomplish a lot of your workload, right? In data analytics, that's 99% of data workloads. You really don't need a cluster for. So your one single machine plus a powerful single node system usually can win on things like cost, latency, reliability even, and definitely productivity for developers. But here's the twist. People are not necessarily doing this, right? A lot of people are still using Spark cluster to process 50 gigabytes of data, right? We still see people kind of, either over-engineering or over-building systems for, simple workloads, or we see people kind of choosing to use the complicated solution for their simple problems, right? And the question becomes, why? Why are people doing this? So now we have to move one layer up, from our application level into the human layer. Understand, right, what, our own anxieties, our own biases, in terms of picking and choosing the technology that we actually use. And now, here's what I think. To err is human. And this is something that Fred Brooks, I think put together that's very relevant to what we're talking here today, and actually something that Dominic touched upon earlier as well, the difference between essential and accidental complexity. So essential complexity is what you cannot avoid, things that you must deal with when you're building your system. So this includes things like domain model, right, your business logic, and your fundamental algorithm. And this is the building blocks of your system, and you have to do these things. You cannot avoid it. But then there's also another class of complexity that's kind of considered accidental complexity. And this is when you are making your technology infrastructure choices, right? The boiler code that you add to your code, to enable something, and a lot of this operational, system glue that you bolt on in order to get your system components to work together, right? So understanding that and knowing that a lot of times is this accidental complexity that is making our system design and choices painful, I think is quite important before even further thinking about the software design and whatnot. It's okay to make mistakes. We all do. That's totally understandable. However, I want to point out that there are real-world consequences to mistakes made. And now this is an interesting paper, I think, that's very fascinating, that I saw a few months ago, titled Beyond Performance, Measuring the Environmental Impact of Analytical Databases. Right? So basically, it introduced a new type of framework to evaluate the environmental impact, energy cost of running different types of analytical databases. And it introduces this new framework called Atlas, right? So it measures both the energy consumption, carbon emission when you're running the program, as well as the hardware that's actually needed to run those programs. And it compares across 4 different databases in this particular experiment. And here's a diagram that shows the CPU carbon emission for TPCH queries when you run them 1,000 times across different memory sizes, right? And you can see, especially comparing DuckDB, which is a very simple in-process, in-memory database that now can handle 100 terabytes of data on a single node, versus StarRock's, which is a distributed systems. It wins across all of the memory sizes and emits so much less carbon, right? So when you choose to use a distributed system, there are consequences. Every single query you use means a cluster is getting spun up. Energy is being consumed. Carbon is getting burned, emission is happening, and global warming is coming upon us faster than it needs to be. So just think about that, right? And this is not just about database systems. AI systems are not any different. And this is a LinkedIn post that popped up in my feed a few days ago, actually, from a prior coworker of mine at Google. And her question was, curious to know what one day of ChatGPT costs OpenAI in terms of energy in the unit of oven running and water in the unit of bathtub water, right? So the answer here is 1 day of ChatGPT is roughly 1 billion queries, and that is 1,000 bathtubs of water and a year of running 16 ovens nonstop, right? So something that's trivial, like running a simple query, becomes really quite significant and has really, tangible impact when you times 1 billion times, right? So let's address the elephant in the room here. What if I need to do AI, right? I mean, this is something that we really cannot look away from anymore today, right? AI demands data, and these are some of the questions I'm sure if you're building any type of core data infrastructure or infrastructure for AI that you have to contend with, right? People have this scale anxiety that because of AI, things that we believe in or things that we looked at is no longer true. But is that really the case, right? So again, how do we make that decision? We talked about this. We're going to have to go one layer, back down from the human to the application level. Understand what are really the workloads that teams are actually doing, companies are doing, for their customers to solve use cases, right? And then from there, it will guide our system architecture or design choices. Right. So let's actually go ahead and look at some of the AI workloads. Now, this is not an exhaustive list, but I do believe that it covers a lot of the common AI workloads that exist there that I've seen. Now, the first one is embedding generation. So, very simply, from your text, audio, video files, and whatnot, you want to generate embeddings, which are kind of dense vectors representing this data, and you store them somewhere in a database, and so you can use it for things like semantic search, RAG pipeline, and a variety of different applications. Now, to take some notes over here, this type of workload, if you pay attention to it, often involves millions of small independent API calls to the model, the AI model itself, or some type of API calls. And it's latency sensitive, right? But this type of workload is highly parallelizable. And they're rather independent because you're just kind of firing up different API calls to get results back on your embedding. And oftentimes, this type of workload is quite bursty. So you have a few hundreds API calls fired up at once, and then it goes idle. Right? That's it. Right. And then once you have these embeddings, the next natural thing that you might want to do is to run batch inference over these embeddings, right? Actually figuring out to predict things using what you already came up with from your prior step and generate predictions. Again, something used in recommendation systems often, and semantic search, like we mentioned earlier. So anything that you're kind of trying to get meaning from your data. And again, if you observe this type of workload, you realize that each record, right, is independent from the other. There's not really any shared states amongst all of these operations. And they can be safely split across your threads, your processes, and even GPU batches. Right? And this type of workload is oftentimes CPU or GPU bound. And sometimes you have I/O waiting in between when you're trying to load your data or figure out the model weight in between. And now, moving from the unstructured data world into the more structured data world, feature generation for tabular data is still one of the very common use cases for very classical, traditional machine learning workloads, right? So basically, this just means you have tabular data, and then you want to create additional features, additional columns on top of what you already have. And those columns can be additional statistics. It can be feature interactions, calculating from existing columns, or any type of temporal patterns, per day, per week, whatnot, right? And this type of workload usually operates on 10 to 100 gigabytes of data, right, which can easily now fit in memory using modern hardware. And there's not really distributed coordination needed because they're quite independent workloads, and it happens oftentimes in short bursts, right? You're running some type of offline pipeline to do this, or you're running in some type of notebook development environment. And then finally, the last workload we'll look at is quite popular these days, right? That's prompt evaluation. That's very common in LLM ops. And basically, you're trying to evaluate a ton of different LLM calls at the same time, compare their performances, running some type of benchmarks. Then this type of workload is oftentimes, again, stateless and extremely parallel. And they can happen in short bursts when you're firing you're doing something, and immediately you're evaluating everything together. So happening in short bursts, thousands of calls, in a few minutes, and then the system becomes relatively idle again, and it's rather lightweight and repeatable. Right. So if you now observe the kind of characteristics of these AI workloads we just talked about, now going from myth to reality, these workloads are highly parallel, right? They're stateless. They don't need to talk to each other. It's just a bunch of tasks that you have to run, immediately, concurrently together across your threads. And it will work, and they will complete. And they're typically small to medium sized because you can batch them up together or kind of chunk them. If they're large, you can break them apart because they're highly parallelizable. And typically, they're bursty and not continuous. They comes in kind of like spikes as opposed to, keep streaming in, with more and more things happening at the same time. So, if we think about it deeply, the kind of architecture that can power this type of workload is better to be something that fans out on a single node, as opposed to spinning up, right, a kind of messy, complicated distributed system, because you can do it. And let's kind of, make it more concrete and think about an actual example of suppose, we're actually running an e-commerce platform and we want to convert 10 million product titles into embeddings using some type of model like a sentence transformer model. And then we want to store these embeddings for semantic search later. Very common kind of AI use case and the first type of workload that we talked about earlier. Like traditionally, right, if you just kind of default to distributed and reach for that overbuilt approach, you will spin up a cluster of 5 to 10 machines, and each with its own runtime environment. And then you probably want to like load these titles from remote storage, like S3, into your machines. And then you will distribute these tasks and then execute the models across all of your nodes. And then you may have to serialize some intermediate results, and you may have to manage the state. If something fails, you have to kind of worry about your cluster-wide retry and how do you handle failure scenarios depending on where things failed. You have a cluster to manage and whatnot. And then you write everything back to a distributed store. When you do this, notice that we're dealing with 10 million records here, which is a few gigabytes of text, and which means 20 to 30 gigabytes of embeddings when that embedding is done. And the consequence of doing this really is we're incurring quite high cloud bill. Right? When you're running kind of a distributed setup over here, you do have to pay for all of those cloud VMs, right? And currently, for example, my distributed query engine, costs quite a bit of money, depending on just how many nodes we actually need to fan out to. And we do have to deal with the network overhead, within our cluster, things have to communicate to each other, and you have to wait for these machines to come up, right? And also, it takes time for them to terminate. You have cold start problem, and it's slow to iterate. If something changed in your data set or you want to try something different in your model, you have to, again, wait for your machinery to get powered up and ready. So not so awesome, right? What's potentially better, if you think about solving this problem differently, is to consider, fanning out this workload on a single node. Because we can choose now to use a 64-core machine, something that's very readily available, you can get from Amazon, and you can split your data into chunks, batches of 10K or 100K, and then you can launch these parallel tasks within the nodes, and now they can start executing. You may have to, you may want to write your own scheduler to really optimize this parallel task execution, but again, that's not something, it's unsolvable, right? And all of these workers would operate independently on local memory and disk. And the nice thing is the workers can even load shared models, right, or cache data in RAM without any serialization or duplication. And finally, you can still choose to write your data back into distributed store, or you can write that directly to local storage, that's fine, and then kind of load everything back up to cloud object storage. So this model is a lot simpler, right? Your entire workload would complete quite quickly, within 3 to 5 minutes. And the code is really simple. You don't have a cluster to maintain. It costs $1 to $2 really to run something like this. And there is no shuffling needed. There's no data, shuffled, like partition sharded across your cluster. You don't have to worry about distributed kind of retry semantics and global rescheduling or orchestration things across your cluster. It's just easy to run, it's easy to debug, and you can scale your instance up, to quite high these days. You can get an EC2 instance with 192 cores, I think a few terabytes of RAM these days, so it can power this type of workload, if needed. Much better. But then you ask, as a very astute listener now, what about reliability? Now, this very famous thing that was coined by Randy Bias in the beginning of 2010s, says that treat your servers like cattle, not pets. Right, that makes a lot of sense. And the basic idea here is that cloud-native compute instances need to be destroyable and immediately can be replaced. So they're more like kettles as opposed to unique snowflakes, with names and emotional attachments, right? So that makes your system more resilient. And that kind of makes you feel like the single node system, okay, is awesome with regard to simplicity, easy to run, easy to manage. But then, okay, are we trading off fault tolerance and reliability over here? Because it's kind of drilled into us that reliability comes from distribution, right? Single node means single point of failure, and that's not so great, as a seasoned software designer. So the question becomes, is single node not robustness? And does distributed system immediately, gives you robustness, right? This is a really fair question to ask. But again, right, I encourage us to revisit the type of workload we're trying to solve for and what we're dealing with at hand here. The first thing is these tasks are stateless, right? So they are actually easy to retry. So if something fails, the reality is you can just retry that particular task. You don't have to actually worry about your cluster-wide retry semantic. And your job doesn't have to wait for every single thing to finish. They're quite independently run. So in some ways, your fault tolerance actually has that type of isolation. And in fact, this gives you better resilience and better robustness in that sense. And remember that modern machines are actually quite stable and powerful. Right? AWS does give you this very nice, cloud-native infrastructure that's at your fingertips that you can use. EC2 machines, for example, comes with, I think it's called ECC RAM, that automatically detects problems and fixes them. And you also get, very redundant, RAID-backed NVMe storage these days. So the modern machines, right, they actually are stable and powerful. So when you run your workload on this type of nice modern machinery, it's nicer to have one thing to manage as opposed to, multiple things that may fail that has just more failure domain and more possibility of failing with different types of combinations. And another thing is, there are strategies, to kind of resume when you fail your workload, right? You could durably write your intermediate output to something like object storage, right? So if something has failed, you can quickly resume from where you started. And it's not really something that you cannot do easily in a single node setup, right? As opposed to doing something like distributed snapshotting, which is a lot more complicated, right? So this is something that you can accomplish. So you realize, really, that this type of reliability concerns and this robustness problems are actually engineering problems. They're not really like a distributed scale problem, right? So it comes down to just good engineering and kind of building resilience by design, as opposed to trying to just use the distributed system, the scale-out pattern to fix all of your problems, because oftentimes that introduces more problems. So I would rather say that we can treat our servers like rubber ducks, which is really the similar vein as treat your servers as cattle. But what we're saying here is, okay, we can just spin up another mother duck, another rubber duck over here, right? If something fails, you just float another one into the bathtub, right? No harm. Retry that and quickly finish the task. Nothing is really changing any of your system reliability aspect. But then you ask, what about long-running jobs? Like all the things we're talking about feels like, okay, quite good for ephemeral things. Things complete right quickly. You can, if your server died, you can spin up another one and retry that task. Okay, if that finishes quickly, that works. But what if my model training task or whatever I'm running takes not minutes, but hours or days to finish? Then what, right? Does your treat your server like rubber duck idea still work? Right. So again, right, this is an engineering problem. There are strategies that would help manage this type of long-running jobs. So I think the fundamental thing here is not about keeping a connection or keeping a process open uninterrupted for 6 hours, right? The idea here really should be, how do I break this task down into 6,000 parallelizable tasks that are retryable, and when you run these tasks, you keep track of their progress. So if something is wrong, you are able to quickly retry that, right? So strategies include chunking, batching, breaking things down into roughly equal sizes so you can parallelize that workload, checkpointing, to durable storage, like we mentioned earlier, making sure that your tasks are idempotent, so they're safe for retry and double processing, and building out this fan out plus merge pattern, so you can fan out your tasks and then eventually merge back the results together, so everything still works. And then using things like time-limited containers, so you can auto restart if your system crashed, right? So again, it's not really about keeping something never fail, which is a really difficult thing to accomplish, but it's about building your system to be resilient by design, and how to achieve that. So now, in our example from earlier, instead of converting 10 million records, right? If we now try to process 1 billion product titles, which makes this more long-running, although frankly, on a modern hardware, depending on how much money you're willing to put into that hardware, this task can be still accomplished within a few hours as opposed to days. But the idea stands the same. This fan-out on a single node approach, still would work, because what you would do, as the software engineer, is to split that 1 billion titles into chunks, perhaps 1 million titles per batch, and then you would process each chunk independently. There is no need for coordination because that is the nature of the workload. And you will load these 1 million titles, embed them, and then store, save that to disk or in S3, and then move on to the next chunk, right? And then you could fan out this process across your cores, and then each process will run independently, write the output, and then exit. So the point here is you can repeat this until your 1 billion titles are processed. And you're doing this chunk by chunk and step by step. You're not, you don't have to do this 1 billion kind of all at once, right? So if something crashes, you can then just retry that chunk that failed. So here, with this model, right, there is no really shuffling needed, no distributed coordination needed, no clusters to spin up or tear down. You can probably have a cold start that's in the range of milliseconds as opposed to minutes potentially. And your 1 billion embedding can be done in 30 to 60 minutes, depending on the hardware that you actually provision. And it's just faster, it's cheaper, and it's a way simpler system to maintain and to reason about if something does go wrong with it. So awesome. And you can see we can achieve quite massive scale with the rubber duck simplicity. But now, of course, the question becomes, when should I build a distributed system in this AI-driven world, when AI is involved? Well, I would say there's definitely use cases where distributed systems are still very helpful in many different AI use cases. For example, we didn't talk about actually generating an embedding model. So training something like ChatGPT's GPT-4 model from scratch, that is a sequential kind of process. So when it comes to that, it's very difficult to break things down into parallelizable tasks and then fan out on your single node. So you might take advantage, of using a distributed system to speed it up. Because again, time is yet another dimension that we oftentimes have to consider when we build software, right? So sometimes you don't want to wait for a long time, for the task to finish, and using the distributed system would help with that a lot. But again, hardware, remember, is gradually, actually quite quickly changing and advancing. So all of these assumptions and these fundamental things that we believe in are changing as we go. So I think fundamentally, it's not about not going distributed. It's really about, when do I need to do it? Does this actually fix, help me address my workload problem, fix problems for me, as opposed to introducing more failure points, failure domains, and complexity into my system. I think the principle of avoiding accidental complexity as much as you can still stands, whether you're building a single node system, fan out on the single node system, or building a distributed system. And I'm actually running out of time, so I will actually not go into the distributed system aspect of the talk as much, but I believe the next speaker who is joining us after lunch today will go into a lot of details in building distributed system to solve very large scale problems when you're dealing with exabyte scale of data and analysis. So yeah. I would say, choose carefully, think carefully, and be thoughtful in your system design choices and adoption choices, so your future self and the planet will thank you. So yeah, thank you so much.